Hello everyone. Um, let's wait a bit for some people to come. Okay. Welcome to another stream of if this is going well. Yeah. Of us developing a Go game engine, hopefully 3D. And yeah, let's see more space here. Doing it from scratch, essentially, more or less, and streaming it all live for fun and of it, maybe. Yeah, to learn and have fun. Okay. So, today we'll continue from last time, where I think we finished. So we finished the input system, and then we started doing some shader stuff. And let me zoom in, where we were writing some vertex and very simple fragment shader. We didn't use them yet, but we did start loading everything. So far it's not really structured, and maybe we'll work on that a bit today to actually structure this more nicely. But at least we have the structure now, like we know the code needed. So we're reading basically our shaders from a resource folder. In this case, we just have one shader that doesn't do much. We create a shader program on OpenGL on the graphics card. If everything goes well, we create two shaders. So a shader program involves or like contains multiple shaders, and in this case we just need a vertex and fragment shader. We're not doing more, but we might in the future. And then we convert these shaders that we read into strings that OpenGL can deal with, which are basically C strings, and then we just load them. So we're saying, okay, here is the source code for the vertex shader, here is the source code for the fragment shader, and then we compile both, and hopefully we don't get errors. If we do, then we can extract the errors using this by essentially seeing if the compilation failed. If it did fail, then we can see, okay, how long is the message queue, and then, or like how long is the message that we get, and then we just read it out. Right now, don't like how. Okay, let's just get the full screen. Okay, and then yeah, and we just print the error message if we find it. Now that we have compiled, we just attach them to the program, and we attach and we link. And actually, once the shader program is linked, we don't really need the shaders anymore, because this program is the thing that we use going forward. So these two shaders that we created here can actually then be deleted, and we just keep the program. Now, this is all in one folder. It's all hard-coded, so we just need to structure it a bit. That's what we'll do today. And then we can go on to actually drawing some stuff today. So yeah, let's see. At least we'll draw using the classic way today, and then we can go and use vertex buffers and whatnot. All right. So let's see, what do we have? So we have a shader, and a shader can include multiple shader program, and a shader program can have multiple shaders within it. So I guess our shader program can, let's see, shader program. So a shader program as a method can have, I think, add shader or like link shader. Attach shader, and then link. So it can attach shader, and all we need really, because we assume we'll take this outside, so we have our shaders and shader program, we just need the IDs. So all we need is shader ID. Yeah, shader ID, that's it. I don't think we need more. Okay, shader ID, and that is an int uint32. Yeah, 32. UN32 is a pointer essentially. All right. So we need to attach shaders with the ability to link, which we don't need any inputs for. And then let's see. Just check that. All right. Link. Now this is the shader program. I don't think we need much more really. Well, destroy. For now, we don't need. We can say destroy if we want to delete. Now, besides that, we need some functions for shaders themselves. So we want to be able to essentially create a new shader and compile it. Load, yeah. So let's make a function here. Load shader, and it takes a shader path. All right, and returns the ID, I think. Returns an ID, and should we return an error? I think we should. Oops. All right. So in here, we do actually need to know the type of the shader. So let's put that. So let's define a constant. Let's just have this here. So shader types.go. Can essentially make an enum. So type shader type is an int, I think. So what does GL use? Yeah, it's an int. So it's an int, and then we can say define some types of vert. What should we say? Vert shader. Vertex shader type equals, which is a shader type, equals GL compatibility. What are we using? Yeah. GL.vertex shader. There we go. And then we have the fragment. Oops, can't type today. All right. Fragment shader type, and that's a fragment. There we go. Cool. So now we can take this as input, just so that no one sends us garbage data, or to help with that at least. So shader type, because we'll need this to run on OpenGL. Shader type. There we go. Nice. So now you can take this shader text. So become system shader source. Right. Now here, this is actually just our path. Shader path. Cool. Field tree shader. Let's take more. Yeah. Error. That's good. So we can log. Then we can return 0, means we didn't get the shader at all, and then the error. So cool. So now we have the source. We need to compile it, right? So create shader. There we go. And here we just say it's this shader type. Shader. Right. And the conversion works fine because we already defined it as an int. Even the even GL defines it as that, so this should work. And that's our type. This will be fine. Now we get shader ID. Cool. Now, if the shader ID is 0, that means something happened in the program. So we need to check that, and then we need the compilation. Just say if shader ID equals 0, then And just say, if it was this fatal, this needs to be just an error. Print, yeah, just print line. Print line, failed, create, shader, error, it's this. Actually just, yeah. Maybe later, I think there is a way to read, just like we write the info log. But normally, I think this shouldn't happen. This shouldn't really occur. Now, return this, and I think errors new. You can just save this thing. There we go. Cool. So we have our shader. We have the shader source. We can compile, which is this part. These lines. Okay. There we just have shader source. We null terminate it, so it becomes a proper C string, and then we get shader C string, and then shader free, and we can free this. Basically, free up the memory, so we don't have a memory leak. Okay. Let's take this one. Cool. Now we need the shader ID, which we got. Awesome. So we're loading the shader source. Now we need to compile it, which is this. You can say load shader source and compile. Okay, compile shader again. Here is our shader ID, and we were just checking for errors, so just press it again. See if we got any errors. Actually, this is not returning the error, so let's make sure we return a go error. And yeah, I guess, yeah, let's return all of this. Errors new. Shader ID failed. Actually, let's just give the error message. Why do we? Yeah. I mean, I guess we can log it. Logging or log or print line. Just this thing. Back. Yeah. Logger. Yeah, print line. So it just prints for now. So we always have it printed, and then we can handle errors in somewhere else, or give a proper message, or log it somewhere different. Yeah, and then the error is the error message. There we go. And then to the outside world, we just return the actual message. Okay. So this is good. And here we can return null because there is no error. Everything is good. Awesome. So in this case, if there is an error, we should return it. So if error and error is not null, then we can return that error because we failed to load the shader. Okay, so compilation succeeded after this. Creating, loading source, compiling. I think that's it. Yeah, then it's just attaching. So by this point, we are done. We can actually return the shader ID and now it's going to want this. What's wrong? Okay. Sure thing, go, sure thing. Okay. think we have a small leak here, which is if we create a shader and then fail in doing the rest, then this shader leaks. That is the ID. So we need to clear it. We need to clear this. So I think, yeah, that's the only place here. We can do the destroy, clear, not clear, delete. Yeah, delete shader. There we go. Delete the shader objects and can just pass the shader ID. So we do a cleanup. If we failed in compilation, then doesn't make sense to continue, right? To keep the shader alive. Otherwise, it's good. Right? So now we have this, which is very nice. Maybe it would make sense to actually give this a struct as well. So perhaps something like shader. So just a shader and shader program, because we can have our ID as usual, but then we can have a shader type. Shader type, which is a shader type. Yeah, that makes more sense actually. So we always have the ID linked with the shader type. I think that makes a lot of sense. So we return a shader. Going to be a pointer, it's just 2 ints essentially. And here, yeah, so here we're returning just an empty object. Here we return an empty object. Here as well. And then here, return this with the shader, with the ID being shader ID, the shader type being whatever we got passed. Where we go. So now we have a method to actually load and compile an OpenGL shader. This is very nice. Now this is all reusable. We don't need all of this code. We need 2 lines of code now instead of all of this. So in our main, so we don't need this. None of this. We moved it. We're going to use this function. Awesome. Let's comment these for now. Cool. So we have this. We have a shader. Now shader program. Destroy. I guess we can just do delete shader. Does it delete a shader and a shader program or not? I'm not sure. Let's see. Let's see what the internet says. So delete shader program OpenGL. GL delete program. Okay, delete. Okay, there we go. Delete program. And then we can just give sp.id and we're done. It should be good. I don't think it returns anything. Yeah, just delete it. Awesome. So that's done. We can even do it here, honestly, since we have a shader. Might as well make use of it by implementing a function method, which is shader. It's not really a pointer. I don't think it will usually be used as a pointer. So just a shader, which is delete. Let's follow the same terminology. So it's delete, not destroy. Delete, and here we can just do gl.delete shader, right? And we just give the ID and we're done. Great. In attach shader, there isn't really much. It's 1 line. It's very easy. Attach shader, we give our own ID, the shader's program's ID, and shader ID. There. That's it. Why are you? I think it's just being weird. Okay, so that's done. The last thing is we have a link. And the link is just this. Then we can remove all of this and add a link. SPID. Great. I think that's done. That's a very nice abstraction for now. To make let us really easily have shader. So let's see how to use it. So in main, instead of this, let's just make a function here. That's like load shaders. And just call it. Now, let's see. So we have right now shaders dot. Come on, go. Can do it. Once. Okay. So shaders finally. Shaders dot load shader. Oh yeah, we don't have a way to create a shader program. So perhaps we'll just do here func new shader program. And yeah, it doesn't really do anything, I guess. Just turns a shader program. That's it. And all we do is gl.create program. Yeah, we get the ID. And if ID, I mean, we do need an error actually, just in case it fails. Most cases shouldn't, so let's just be right. If this is the case, then just return an empty one and do an errors.new fail to create shader program. There we go. Otherwise, we can just return a shader program. And what do we have? We only have an ID. There's our ID. No errors. Awesome. Now, yeah, I guess this is okay. Now, instead of passing a shader ID, we have now a shader type, so might as well pass it. A shader, and we have a shader, right? And now we can do shader.id, and we can fill in this. Right, we can fill in this, at least for now. So we can say switch shader.shader type, and we can say if it's a fragment, if it's a vertex shader type, right? We can return or actually set. Let's see. We can set the vertex shader ID to shader.id. Otherwise, if it's a fragment shader, then we just set the fragment shader ID. Right. Default, you can just log a print line unknown shader type. Yeah, no shader type, and we can do the type for ID, and we can just attach the ID. There. This is nice. All right. Now, I think when we link, we can actually think this is fine. So now we can just delete the stuff we have, right? So we link, and then we can say if we have a fragment shader, so if it's not 0, then we can gl delete shader, and we just do vert shader ID. And then if we have a fragment shader, It's on 0. Then we can also give the fragment shader 8. This is pretty complete, I think. We just need now to use all of this. Great. So shaders.new new shader program, and we can get our simple shader, right, and an error. You can say if error null. We can just crash for now. We really can't load simple shader. Okay, so slowly logging error logger fatal line fail to create new shader program, and error is error. Right now we have our new shader. Now we just need to load the two shaders, which will load and compile actually, and then attach and link, and that's it. So it becomes a very simple process from the usage perspective. So we wrote this code once, and now it's easy to use. Let's just rename this because it doesn't actually load, and it compiles as well. Load and compile shader. Right. So we create a program. Let's load shaders.load and compile shader, and then what are we going to do? Resources, shaders, let's log the vertex shader, right? And so we can say, hey, it's asking what's this? We can say this is vertex shader, and then we get vert shader and then error. Same thing, the error, fail to create new shader. And I'm going to repeat this, right? Maybe this is our fragment shader, basically pixel shader if you don't know. Frag.yellow cell, and let's take this. Also, now all we need to do, simple shader dot attach. Let's attach the vertex shader, and then we can just attach the fragment shader, and then we can say simple shader dot link. That's it. Now it becomes very nice. So you can load these, get a new program easily, and create shaders very easily. Now you can run this, and since these would crash if something went wrong, and I think load and compile would fail, we would know, we would see the error. So yeah, I think this is correct. Are we calling this? Yes. Okay, let's call it. Let's run. So this is essentially go build and run. Okay, no errors. Seems to work fine. This is really good. So that's really nice. So now we have a nice way of making shaders. On this shader, we can make it like a global variable for now, just so we can use it in other places. But let's see. Now let's actually get some triangles running before we jump into all the Vertex Buffer stuff, just to get something nice. So if we look at the old way of doing it, yeah, this is the new way. Let's see. Is there one here? Yeah, not really. So let's do OpenGL fixed function pipeline. Let's see if we can get an example, just to test everything we have. Example. Okay. We want some code, please. Yeah, this is not code. There we go. So yeah, that's it. Let's take this, and I guess we can explain it as we go. Okay. And this will help us explain then, once we have this will help us explain how it differs from the old one. So in our draw loop, are we calling our draw loop? Yeah, so we handle inputs, we get all the latest inputs, we run game logic, which we don't have now, but it's just something, and then we draw. Draw is when we actually show everything on the screen, show all the triangles. So if we go now, we can do GL. So first, well, let's do it this way. So we have to tell OpenGL we're drawing, we're starting to draw. This is the old way of doing things, but it will help illustrate. So GL begin draw. Let's see. Begin. Maybe it's just called begin here. Okay. So triangles. So we say that, okay, what are you drawing? So we're drawing triangles, and then I think just GL end. Yeah, GL end. That's it. Now in between this, so we're saying, hey, we're drawing some triangles, and here are the triangles. And so if you remember from last time, we actually said this looks too big. Okay, so if we said we have a triangle, and that's like our screen. This is not a straight line. Okay, so if this is our screen in OpenGL, the coordinate system is the center of the screen is 0, 0, right? And I think as you go right, X increases. As you go up, Y increases up to 1, 1. So this is 1, 1. Right? This is -1, -1. So no matter the actual resolution, we have kind of a normalized coordinate system. So we can place these points. If we say I want a point 0.05, 0.05, so it might be on this one, or might be somewhere around here, right? And this could be 0.5 on the X, 0.5 on the Y, so it's halfway. So we need to define 3 points, and we tell OpenGL, okay, here is my triangle, here are the vertices making it the position of each vertex. And then it will by itself, draw and then color the triangle. So now we need to define a vertex there. Okay, 3F vertex 3F. Okay, so 3 floats, but right now we're not using depth, so they're all going to be 0. But we could say, so let's draw it like this. So like, a proper triangle centered triangle. So let's try to make one that kind of looks like this. It's just me move these. So if this is our window, maybe we want a point here, point here, a point here, and then this is essentially, this is a bad triangle, but this is how our triangle is going to look. So this one is centered, so 0 on the X, I think, and then halfway up, so 0.5 on the Y. This one is the opposite, and this one is minus 0.5 on the X, again 0 on the Y. Yeah, let's do this. So on the X, so let's start at the top, go clockwise. Usually you have to follow some kind of scheme. We see later that some cases doesn't matter, but okay. Centered up, halfway up the screen, and then let's just put Z as 0 for all of them. Okay, for the other ones, so then we need the next one is on the right. So it's 0.5 on the X, 0 on the Y, and then minus 0.5 on the X. So that's the last one on the left side, like this. So telling, okay, here's a triangle, take these, and right. So let's see if this actually works. So run. We don't see that. Okay, maybe the screen is also just, right. So we can clear the screen. So GL clear. Can you see the bits? I think this one. Color buffer bit. Oh yeah, we need to swap the buffers. Yeah, because we double buffered it. Let's see. So let's make our background white or black. So what did we set our color? Did we set it? So our pixels, we double buffered. We didn't set what we need. Okay, yeah. GL set attribute. So you can say what is the clear buffer. So I think it's something like SDL dot clear. Let's see. GL context. Buffer size, frame buffer. Okay, then maybe it's GL dot buffer. Clear buffer. Clear color value. See bits. Current bit depths. Clear bits. Okay, let's see. OpenGL clear bits. GL clear. Okay, we clear. Okay, clear color. Okay, there we go. So this one we set which color to clear with, and then clear actually clears it. Okay. So it's called gl.clear color. There we go. So the clear color, let's say it's all black, right? So far our screen is white, so this is black and full alpha. Is it 0 to 1? Initial values are all 0. All 0. Okay, yeah, it should be in the range 0 to 1. Should be already black. Let's see. See if this looks black. GL clear. Ooh. Now, what do we want to clear? We want to clear GL dot clear bits, or what is it called? GL color buffer bits. Color buffer bit, yeah. So basically clear all the pixels. Return them. So clear basically returns all the pixels to whatever the clear color is. Right? So we're saying, okay, all of them are 0. So even if we colored them the frame before, now we are resetting everything to this. So we can draw a fresh screen. And we can see, once we get this working, what the effect of not having this switched on, which we'll see like essentially a drag effect. Let's run. It's still so light. Let's make sure we have compatibility mode on. It is. And let's just make sure we SDL swap. The GL swap? Yep. So GL swap. Let's see. We need to swap the screen. Build program, we finished. Yeah, we need to swap. We need to tell SDL to swap the screen. So let's see. I think in the window. So maybe window swap. GL swap. Okay, there we go. Updates a window with OpenGL rendering. All right, let's see. All right, nice. That's amazing. So this is our first triangle, and I think we can see this essentially the x-axis. Our first point is halfway up, while these are exactly on the x-axis since the y is 0. But one is to the right, one is to the left. And then the background is cleared with black, and the actual triangle is white. Now we can start playing with this. It's very nice. That's good progress. This is, of course, the old way of doing things. We won't be doing this going forward, but it's a good start just to get a feel of how everything is working. Now, so again, what we did is we set a color for the background. So we have two buffers. we have two buffers, really. So our window where something is currently drawn. Let's say this is just the start, right? And we don't have anything on the window itself. So nothing, this is empty. This is empty. And this is what's currently shown to the screen, right? Now we have an exact window. So this is shown outside. We have a window of the exact same size that's hidden, right? And this hidden one is called the back buffer, essentially. Now, when we draw, we are going to draw to this one, and essentially the user won't see what's happening, won't see what we're drawing, and so here maybe in this frame we draw a triangle, right? They don't see the triangle. So maybe this the first screen, right? Let's do red. All right. So maybe this one has a bunch of red here. Now what this is going to do, first we're clearing. Every time we draw, every frame, right? So maybe 60 times a second, we clear the colors. So we're saying, okay, imagine this one and this one started out the same. There was some color here, there is nothing else. So we clear it, we reset all the pixels to some default color, which is in our case black, right? So this is going away. And then we're drawing this, all of these. So we drew the triangle, but still this is not seen outside. So whatever is in the triangle in our case is going to be, not sure why this is not switching, but okay. This is all going to be filled up, white, right? Filled up. It doesn't have to be, but in this case it is. You can configure this on OpenGL. And now we want to show it. We're done drawing. We want to show the user this result. So we call, the last thing is, we GL swap. So we say, okay, switch these two. This shown one is going to be hidden, and then this previously hidden one is going to be shown to the user. And then next frame, when we start drawing, we're actually going to be operating on this one, right? So let's play with it a bit. So now let's move maybe, because our triangle is kind of squished. It's only half the screen, half height. So let's push it down. Make it minus 0.5 on the Y. Minus 0.5 on the Y. Let's draw this. Nice. So so this is now looking nice. Now let's do some coloring. So our background is set by the clear, but what sets our triangle? And this will be important actually when we start doing more into the programmable pipeline of the GPU, because we deal with all of this. But essentially, every vertex of the triangle. Why do you not let me switch colors? I actually don't remember the should be X as a shortcut to switch colors. That's fine. Okay, let's do some blue, light blue. So let's say we have our vertices. In this case, we give our vertices, and this is the minimum position values, because otherwise it doesn't make sense. So the vertex doesn't have position. Any vertex can have attributes, so additional information for each single vertex. So here, along with the position must always be there. I can say, hey, there is this color attribute, and maybe your color is, if I like RGB, we can say something like 0, 1, 0. So that just tells us, okay, this at this specific point, the color is exactly green, RGB. So this is green, right? This one is maybe if we define this as also green, and this one also green, so we're not only passing to the GPU the position of the vertex, we're also passing additional information that it can understand, including like the color, which is a standard one. And so the GPU is going to interpolate this color and fill in. So if the pixel is closer to a green vertex, then it's going to be green, and the further away, it's going to be affected by the other vertices. So you can try this, just like this example. We can set some other attributes like color and then the vertex. So we can do this. So for this vertex, right? So for this one, we're going to say GL, actually just color, yeah. GL color, and we can say it's float. So between 0 and 1, we're going to give, let's make it green. So 1 non-green, fully green, 0 blue. Same thing for all of them. Right, that's it. So say here's an attribute, here's some information, here's the actual vertex, the position. Then again, some other information. So each vertex is now having basically double the data on it sent to the GPU. More information. Let's see a green triangle, hopefully. There we go. Nice. Now, what if this is called vertex coloring. Some games use it because it's just so easy, so very quick. If we change this value, let's say one is green, sorry, this one. One is green. What if we make the other two white? So let's just fill them up white, right? So we have the bottom two white, the top one green. The GPU is going to automatically interpolate the color of the pixels. We have a gradient now. So where it's closest to the green pixels, basically fully green, and then as it goes down, closer to the other pixels, it gets kind of averaged between all the available pixels. Now, we can even give each one different colors. So one is maybe top is red, right? This one is maybe green, and this one is blue. And we should see full gray. Nice. And this is one of the classic example. It's just simply 3 vertices, 3 colors, different color on each, and then the rest is done by the GPU automatically for us. Right. Now let's do let's see. So let's do not a triangle, but let's do a quad, like a square. Right. So a square. Now we basically almost always draw with triangles. So if we have a square, we cannot tell that the GPU, okay, here is, here is a vertex, here is a vertex, so on. It doesn't understand this. It understands only triangles. But if we cut this thing, so we can see there are 2 triangles here. So one rectangle or one square is made up of 2 triangles that share 2 vertices. So these are shared between triangles. So let's see. So this point, if we have a window, we kind of have the window right here. So this is the center, right? Somewhere around here. So this is minus 0.5 minus 0.5. This is 0.5, 0.5. This is 0.5 minus 0.5. Then this thing is, actually this is 0.5 minus 0.5. Here, minus 0.5. Minus 0.5. So we'll just send these, so a total of 6 vertices. Let's see how it looks like. So let's just remove coloring. Let's just get a normal triangle for now. White. So let's start top left, and we can go clockwise. We'll define 2 triangles. So this top triangle here, and then this triangle here, independently. So let's define this one. So triangle 1 is minus 0.5 on the x. It's up right? So on the Y, and then the one on the far right is 0.5.5, and then the one on the bottom left is minus minus. Okay, this is correct. Right, this should be. Let's see. Let's just confirm. Right. Okay, this is half of our rectangle. Now we need the other three, and so if we start from 0.5.5, 0.5.5 is the first one, and then 0.5 minus 0.5, and then on the far bottom left is here, and that should be enough. Nice. And this is how you draw rectangles. Now if we move, we don't make it symmetric, we can get all kinds of things going on, and we can color them, we can give all kinds of attributes, but for now I think this is good. Now the issue with this really is that this is really slow. This is the old way of doing this, and you can see we didn't get a lot of control either. We can do more, but it's not like we have a shader or we're controlling exactly where the vertex appear, or maybe we want to kind of shift it with time, move it. And in this case, we might have to do it on the CPU by changing these vertex positions. So every frame, we have to send updated positions, which can get us kind of slow. Now, the issue is every frame, every time we want to draw, we're sending all the vertices. So it's the same square. I'm still drawing the same square or the same set of triangles. Why am I sending the same data again and again and again from the CPU to the GPU? Right here, this is the CPU saying, okay, begin draw, end it, etc. So every frame, even if it's the same kind of objects that we have on the screen, we're sending all the data again. And this becomes extremely slow when you have hundreds of thousands, or and then you add on attributes for each single vertex. If you have a complex scene, you're easily in the thousands nowadays, maybe in the millions of triangles. So imagine sending millions, maybe gigabytes of data to the GPU every frame. It's not going to hold. And if you add attributes, now you can multiply the amount of data that you have to send. Sorry. So the idea of, or one of the things that is useful in the more modern way of doing things, which is called, so this is called a fixed function pipeline, where the GPU just does one thing, we cannot control it. Nowadays, we have programmable pipelines with all kinds of shaders like this, where we can write complete functions as much like anything we want, really. This is why we're running in compatibility mode, where it allows us to use the new way and the old way, but potentially you don't want to do that. So we only go with the core mode, the new way of doing things. In the new way of doing things, which is more complex to set up, definitely, but it offers us much more performance and even control. We, just like we created shaders and then we filled them with the source in the shaders package. Let's just close these. Just like we did here. So we're creating a shader on the GPU, we are filling it up, so on. We can do the same thing with the vertices. We're going to create what's called a vertex buffer, right? We're going to fill in all these vertices, send them over to the GPU, and then GPU is going to store them. So we only send them once, and we only change if we need. And then we are going to tell the GPU, okay, draw this set using an ID, for example, draw this set of vertices, draw that set of vertices, without ever sending the data. We're just referencing something that we already sent in the beginning. That way, there isn't really transfer going on between CPU and GPU. It's just one transfer or when needed, and the rest is just control, which is very quick, very small amount of data going between CPU and GPU. And that is what's done nowadays to build all these complex games and 3D software, really. Okay, so let's start. Now we have kind of a good point. Maybe push this to GitHub. So let's add this. So let's say drawing triangle using, or we're actually drawing triangles using fixed function pipe. And I think that's the last time we'll ever see fixed function pipelines, but it's good to really understand what's going on. And then we can completely get rid of this, enable core only, background can remain black. Yeah, all of this goes away. And now we go down a very different path. Now, if we just, this swap, clear and swap is fine, it will work. Oops. It's just going to be black all the time. Nothing happening. We have a shader. Now we want to have data on the GPU that the shader can access. So we're going to essentially, I can close this. This website is really nice, and we're going to be using it a lot. I think maybe the best resource already online for OpenGL, goes through all the details. So we're going to need to send all these vertices that we define the same way. We're going to send an array of them to the GPU, all the points and their attributes, and then these points go to our vertex shader, which then produces the points. Then the fragment shader runs, and then we see the display. So we are going to need a bunch of vertices, but now we're dealing with arrays, so we're going to send a bunch of them all at once. That's the coordinate system, right? Centered at 0, 0. Yeah, there we go. So we are starting with vertex buffer object. So we're going to also abstract this away, just so we have a nice little interface like this that you can just use. I'm not sure how the interface would look like, so let's just do, for now, maybe buffers, potentially. Let's do buffers.go, just to do all our stuff here. Okay. So what's the idea? We're going to create vertex buffer objects, which I think now makes sense. It's a buffer, essentially an array, some amount of RAM or of memory that's available for use. So we have that buffer, and we're going to fill it with vertex information, be it position or something else. So even the color data, we're going to create one vertex object, buffer object, one VBO for the positions, another one for the colors, etc. Right? So let's see. So we're very similar operation to how we did with the shaders, where we generate, we get an ID back, and then we start using them. So let's do it. Just do something random for now. And then buffers. Then, so we write it all in one place to figure it out, and then I guess we can extract it once we understand it better. Okay, so first, let's handle just vertex positions. Let's try to replicate this triangle, but using now our shaders and the modern way of doing it with buffer objects. So let's do gl create buffer. Okay, there create buffer. There is gen buffer. Not sure what the difference is. Here he's using gen buffer. Maybe you can look at this. Create buffer versus gen. Let's see. Oh, okay. Create initializes them. Okay. By binding a name returned by gen buffers. The binding is affected. Oh. Okay. So it seems create buffer is the newer one, which initializes and binds. Okay. Maybe try using that. 4.6 compatibility, and I think this is how many buffers we want. Then the buffer size, or no, that's a pointer to you. And okay, I think that's the ID. So you in 32 var, what do you call it? Say VBO ID, and we pass that, and that should be filled. I think. Yeah, we're creating one, filling it. That seems the only difference really is a new, so it creates it and zeros the memory binds. Yeah, because buffers are not typed. Not sure. Let's just do this for now. Okay, so we create the buffer. Now we need to fill it just like we created the shaders, and we fill them up. Now we can create we created the buffer. Now we can fill it up. So let's see what the function name is. I always find these hard to understand. Yeah, it's bind and then buffer data. Okay, so it's called buffer data. Now, previously I mentioned that OpenGL is like a big state machine. And this is one of the cases where we see why. So this function here, buffer data, doesn't actually, so when we're dealing with the shader program, we always pass the shader program ID. So OpenGL knew which shader program is dealing with when we attached, for example, a shader. In this case, buffer data, which takes the vertices from us, puts it on the GPU, doesn't take an ID for which buffer to use. So it's actually done by binding. The buffer means it's like passing the ID, but in two different steps. Like, hey, I'm using this buffer now. Anything I will do after this is me working with this specific buffer without me passing you an explicit ID. So it's like a state machine. It remembers by this call, it remembers, okay, you bound this specific one. So I'm going to know. And here we're using the type. So let's just start doing this. Bind buffer. Targets and buffer. So type of buffer and the actual buffer. So let's do this, and then we can read array buffer. Yeah. The actual buffer is this, which we just created. And of course, we need to check if VBO ID equals 0. Then maybe for now, we can panic. Print failed. Get let's just do logging. Okay, error log, print line. Okay, so we bind it. Now we can use it to send the actual data. Now we need some vertices. So if we look at the stuff we had here, well, it's gone, but let's do, so our vertices is an array of, let's see, of floats. Yeah, it's an array of float 32, which we can send. Now array buffer is gets the types of buffer objects. Okay, for a vertex buffer object, it's array buffer. Yeah, and it says we can bind different ones as long as they have different type. Yeah, so if we bind an array buffer here, again we're saying, oh, work with the array buffer that I bound, but I can bind an array buffer, maybe something else, and work with them at the same time, which makes sense since they are different types. It's differentiating based on the type. then vertex, get to that. Yeah, this we did all of this. Nice. Attributes is where we, okay, we'll get to that later. Okay. So let's get some vertices. This looks okay. So it's an array. Like we're not sending, okay, here's a vector, here's 3. So we're just saying we just put one big array, and then we're later going to tell OpenGL that, hey, each 3 is one vertex, XYZ, right? So let's say, let's draw the original triangle. So starting at the very top and then going clockwise. So you can say it's 0 on the X, 0.5 on the Y, 0 on the Z, right? So that's one vertex. And then, of course, it's just an array. We can continue here, but let's just do a new line to kind of understand what we're doing. So the next vertex is on the right, actually, yeah, 0.5 on the right, then half down, 0, and then 0.5 on the left, also down, 0. So these are our vertices. Now we need to send them, and this is a nice thing. We only need to send them once, right? And then we can draw again and again using the same ones, as we'll see in a bit. So we have them. Now we just need to buffer the data. Buffer data. Okay. Creates and initializes buffer object editor. Okay. So target is similar to this. Target is just a type, which is an array buffer. Okay. Size. I think size is all the data, not like the size of one float. Go doesn't have size off, but we know this is like 32 bits, so it's 4 bytes. We're dealing in bytes, so this is 4 bytes. So I think we can say 4 bytes multiplied by n floats. So we can say then len vertices. I think so. You can check. Yeah, 4 bytes for each float, and then n of them. Okay, and then where is the actual data? That's our vertices. Vertices. What's wrong? Usage 0. Oh, okay. It wants an unsafe pointer. Okay, we need to change it. Come on, GL, help me. Slice point. Okay, pointer. All right. Takes a slice or pointer and returns GL compatible address. Okay, like some data and okay. So I hope this works. We just pass our vertices. We get vertices pointer. Oh, just I guess we can use it directly. So we're telling OpenGL essentially, here's our data, and here's how big it is, the total amount of bytes taken, and now the type of usage. Let's see, yeah, size of vertices. I think size of, it's on the stack here. Yeah, it's the total bytes. Static draw, and this is if we want, like, I think if you're animating, I'm not sure if you animate on the GPU directly, but how it would be. But if you're always kind of changing the vertices, updating them all the time, then we can do a stream. Not a stream. Vertices. A dynamic. Yeah. So you can say, hey, this data is dynamic. So OpenGL can optimize the GPU usage, right? Static is most of the things that don't move. Only we send the data and then we just keep telling it draw it. And that's it. So yeah, for us, it's going to be GL static draw. Static draw. That's good. That's it. Honestly, doesn't seem too bad so far. Any questions in the chat? No. Okay. All right. So we created a buffer. We bind it we have some vertices as an example. We buffer them. I think that's it. Is there anything else? No. That's it. Now, we need a way of essentially passing those to the shader. That's it. Let's see. Vertex Shader. So in here, so the Vertex Shader needs as an output in the end is a position on the screen. Now, normally, like when we did the fixed function, we didn't do this. It automatically, like whatever position we gave it, it put it on the OpenGL coordinate system, and that's it. Since we have a shader now, we can program. We can actually play with it. Maybe I want to scale it up, so I can just multiply all the positions by something, and it gets bigger or smaller, right? So we can play. We can start like having dynamic content just because that's why it's called like programmable. Now, in the programmable shader, we have an in. So that's the inputs that's being sent by OpenGL to our shader. Let's take this. I'm not going to put a position now. Where's this? Resources. So vertex. So we have this. Okay, we already did this. Not sure about the layout. Do we need it? Yeah, we have one input, which is the vertex position. This being sent, and then in this case, we're just keeping it the same. This is equivalent to essentially this. Right, it's the same as this. I'm not sure what this means, but if you don't want to do anything, you just keep it one. We can check that later. Okay. Let's see. Okay. Yeah, has a vector data type 1 to 4. I don't select the location. We can talk about that. Yeah. Perspective division. So that's the last component. Okay. GL position. Okay. We already did all of that. Create shader, compile, all this magic, fragment shader. Yeah, this is just the color of the output. This is again nice, so we can control the colors not through hard coding it, right, in the code, but directly on the GPU. Because remember, the main difference is all of these, this one, the vertex, and this one, they run on the GPU, not the CPU. So before in the fixed pipeline, we have to set every time. CPU has to say for every single vertex. Now we don't need this. We can just do some maybe math here and keep changing it with time. Let's see. So this is nice. Our output is fragment color. Okay. Let's make it. Yeah. Good casing. Fragment shader. We did this shader program. Yeah, use shader. Okay, so we don't have this, right? We need to do this, and then we don't need these things, which we are doing. So maybe we can add to our shaders, which we'll use in a bit. Our shader program, because you can have, if you have used Unity or something, you can have many shaders in your game. Maybe you have your normal shader, and then for a special effect, you change to a different shader that maybe adds a glow to each pixel or something. So we need the ability to tell OpenGL, okay, right now, just before drawing these vertices, start using this shader and then draw these specific vertices, so we can switch shaders for different objects. So to tell it, now we have link, and just before delete, maybe we can do there, use, right? And then it's going to be use program, I think, yeah. Use program, and as usual, takes the ID, just the ID. That's it. Nice. Linking. Okay, now is the part where we actually use it. Okay. Okay, so we said that we, like when we did the fixed function, each vertex can have a position, right? Always actually has a position. And we can add other things that like we were adding the fixed function, we said color and then the vertex color and then the vertex. So we can add, okay, this vertex is also like 1, 1, 1 or something, right? It doesn't, now in this case, since we're doing buffers, we can, per vertex, like if this is our array, how are we going to send it? So you can imagine like X, Y, Z, right? These 3 floats. And then where do we put the colors? You can imagine saying, okay, you know, after this, you have R, G, and B. And then again, X, Y, Z, R, G, and B, right? So all of this is vertex 2. All of this is for vertex 1, right? So in the inputs to the shader, we don't only have to have vertex position. You can have vertex position, color, maybe some other information that maybe we can use for animation or something. As many as I think there's a limit, but it's pretty big. So we put all of this. Now the problem is to OpenGL, it doesn't understand the difference. So it doesn't know, like to it, these are all just floats, for example. It doesn't know that these 3, right, are position. These 3 are color, etc. So we need to specify, okay, we gave it all the data, but we didn't explain the data to OpenGL. So now we need to explain the data to OpenGL, and I'll tell you, each n bytes is this thing, it's that thing, so on. And this is what we call vertex attributes, right? We have vertices, and then each one has some kind of data. For now, it's just position. And so we have attributes. Let's see. Yeah, for now it's just position. And then binding. All right. So let's just start doing that. So we added, we bound, we filled it. Attributes. Vertex attributes. Right. Okay. Vertex attribute. Okay. Vertex. Define an array of generic vertex attribute data. Okay. So the index is 0. Well, in this case, we actually need to get it. To simplify, let's do this for now, but yeah, this is why I think they use layout here, 0. So each kind of input to the vertex has a position, which we call layout. And then these positions, we don't know the numbering of beforehand. We can hard code them, or we can ask OpenGL, hey, this name, like vert post, what's the position? So we can select an ID. In here, they actually hard coded that. I don't like that. We're going to, yeah, okay, location 0. I wonder what layout is. Location 0. Layout. Wow. Dun, dun, dun. Set the location via layout. Okay. Because they're setting this. So they put layout, and the location in the layout is this 0, 0, 1, 2, 3, so on. We don't want that. We don't want to hard code. We want to ask for it. So we need the position in the layout, right? The location of the variable for the vertex shader, for this vertex shader. The size. So what's the size? This variable is a vec3. So that's 3 floats. By default is a float, so that's 3 floats. So the size is actually the size of 3 into the size of 1 float. And I think we can get from OpenGL what the size of the float is, just in case it's different. Oh yeah, GL float. Okay. Let's see. Size. Okay, 3. Okay. So they're separate. So the size of one element and then the type of that element. No, how many elements? Size is how many elements, and then what is the type? Okay. So we have 3 elements. It's a vec3 x, y, z. So that's 3 elements, and each element is a float, a GL float. So whatever GL float is defined to be, and the size potentially, I'm not sure, but on different devices or GPUs, it's going to be different sizes. Yeah. So we're defining things 3. Normalized, false. We're not doing one normalized. Stride. Okay. So the stride is the difference, the jump between each value and the next. So in this case, for example, I believe, so this is our position, right? Now our next position is not just directly after, because we have color. Let's do blue, right? This is our position. This, there you go. This is our position. Now the next position is all the way here. So we have to skip this. If they are tightly packed, that is just like, okay, 3 and then 3 and then 3, then no need for a stride, no need for a jump. But if they're not directly after each other, then potentially we need to jump over some values, right? In our case, it's packed like this, so XYZ immediately, XYZ after that, right? So the jump from the beginning of 1 to the next is just 3 floats. There's nothing special about that. So 3 and then 32 is 4, right? 4 bytes for 1 float and 3 floats. And then the data. What's this? Pointer? Pointer for what? I'm not sure. Yeah, it's just, he's passing nothing. This is, okay, this is the offset where the position data begins. For us, well, it's all position, so we don't have an offset. Okay. So I think I saw gl.offsets. Yeah, pointer offset. Indicating offset integer 0. There isn't an offset. Awesome. I think this is pretty good. Now we do need to find the position if we're not hard coding it. So you can say gl position attribute location. I think something like location. Find location. Get attribute. Okay, there we go. Get attribute location. So right, this is an attribute. So we want to know what the location is. Program. Yeah, we need the specific program and then the name. Ooh. Yeah, I mean, that makes sense, honestly. So I guess this goes to be part of the shader that we have, right? So the shader is getting bigger and bigger. Let's just move the shader program to its own file. Shader program shaders, and let's take all of this just to be clean. There. Nice. Okay. So our shader program link use. Now after we link it, it's now complete program composing of all of these. So part of it is the vertex shader, and so we can ask questions like, hey, tell me where the attribute is. Get attributes location. Yeah. Now, get attribute location needs an ID, which we have, and then the name. So in here, like the actual just string, here we just say attrib name string, and we return an int, I think. I think we, yeah, it's just an point, let's see. So GL get attribute location. The program is this program. And name, okay, yeah, we need to change the name again into a C string essentially. So str, and it returns compatible address. Yeah, this looks good. So the caller must ensure string is not garbage collected. I guess that will be fine. Or should we? I think it would be safer to free it ourselves. Yeah. And returns the counterpart. Let's use this simpler. Okay, so we give the attribute name. And that's it. There's returns an int32. Okay. That's good. Handle buffers. Let's just take SP shader program. So we take a shader. Like for now, we're just trying to write one function to play with all of this and understand it, and then we can break it into proper abstractions like we did with the shader loading. So, right. So now we don't need this. So we can query the shader itself and tell it, hey, get attribute location, tell me. And we want which attribute? So we want vertpods. Simple. We do need error handling potentially, but for now. Vertpods. There we go. Now it's more correct. Shorten this to get attribute. What's wrong? Oh. All right. So we're getting the location. We do put it here. In this case, we know it's a float, right? So we have 3 floats. The jump is just 3 to 4 bytes, and then no offset from the beginning of the array. Perfect. We're almost done, I think. Enable. I think here, I think they're just disabling it. They're like basically saying, okay, we're done. Or actually, they're enabling it to use it to tell OpenGL, okay, start inputting this data to this variable. Each vertex attribute from memory managed by VBO. Okay. You can have multiple VBOs. Yeah. By the VBO bound to okay. So this is something that we need to be careful of because the VBO needs to be bound. Yeah, that makes sense because we buffer the data. Now imagine these are in 2 separate places. How does it know which VBO? We can have multiple VBOs, one maybe having vertices, one having something else, like positions, maybe one having colors, etc. How does it know which of these is going to use for this variable, the vertex position? And it's going to know, because again, it's a state machine. So it's remembering that, hey, the bound one is this. So we bind it, and then, of course, here we buffered and set the attribute in the same step. Does it have to be? Maybe we bind and buffer, and then later on we bind again, and then point to a variable or assign it essentially. Yep. We need to enable the attribute because they're disabled by default. Okay, that's easy now. Enable attributes. Vertex array attributes. Attrib array. Enable vertex attrib array. Okay. Generic vertex attributes array, and we just give it the location. If I'm not mistaken, it's this. Yeah, so we bind and fill, and we set this information to this specific variable, and we enable it, enable the variable. Then we can use and draw. Awesome. This looks nice. Okay, let's try to draw something with all of this. Now, so this should be good. And let's make this public. We call it, yeah, and since we assigned this data, all of this data, so here create and fill vertex buffer object, right, up to this point essentially, and then assign the VBO to Vertex. Now that we have this, if we run our shader next time, it should be just using this information. So only once now. So this is one of the differences. After we let's collapse this. After we load our shaders, we can say, hey, handle buffers dot handle buffers, and yeah, now we this shader, this simple shader, we actually want it global. So let's just have a variable here, simple shader, which is a shader program. Yeah, and then we just equal. Okay, that's it. So now this is set, and we can pass simple shader, and I hope this actually draws. So now I think every time, so this fills up all the data. If everything is correct, we can clear, and we can simple shader.use, and then so now it's using, and then yeah, so we clear, we start using this, we tell OpenGL, okay, use this, and now we just need draw. We need to say, okay, now we draw this set of vertices, because we can use the same shader on many different objects essentially. Vertex array, I don't think this is needed. This is an improvement, but we don't really, it's the same process. Bind, yeah, let's do triangles immediately for now. Use program, bind, okay, there we go. Bind the vertex array object. Okay. Okay, I think we can directly bind a 0 to 3. I think we can directly draw with with VBOs. VGL roll VBO. Yeah, without a VBO, we can look at next time. Let's run for now. Let's just see if we crash or anything. Yep, we do. Locked thread. Missing null. Oh yeah. We did null terminate. That's correct. So in our shader program, we have to null terminate. Like this. Yeah. Okay, seems fine. So we're having the clear, but then we're not doing anything. Okay. Can we or can we not? Okay, enable. See if this can help us. Display clearing. Okay. We will get into matrix models. Matrix later. Bind buffer. Okay. Vertex pointer, color pointer, draw arrays. Is that enough? Bind buffer. So then they zero and bind. So maybe you can try this. Sure. So we buffered. We already have the correct array bound. Can we do bind vertex array object? No, that's VAO. Okay, draw arrays. Draw buffer. All right. Render primitives from array data. Specify which color buffers are to be drawn. No, not that. Yeah, let's try draw array. Mode, it should be triangles. So gl.triangles, I think. Right. And first is 0 up to, so how many vertices do we have? 1, 2, 3, that's it. I'm not sure this is correct. Let's see. Oh, it worked. Nice. This is now the modern way. We still have VAOs. We can look at next time just to combine, basically combines a bunch of attributes together. But this is now very, very good stuff. So after all of this work, we're actually using our shaders. So our vertex shader is outputting stuff as is. And then we have 1, 0, 0 on the fragment shader. That's why we're getting red. Now, if we make this all ones, the shader, get a white triangle. Awesome. Yeah, I think this is really, really good. So we did all of this work. It's kind of maybe confusing, but it's not too bad. So this needs to be abstracted a bit more. What we'll essentially do maybe next time is we will use VAOs. It's like here we have one buffer, but what if we have multiple buffers, like one for color, one for position, one for, I don't know, UVs or something. A bunch of them might be related. Like for this set of vertices, these are the colors, these are the UVs. So to kind of group them without binding a billion things. So this is working because we're binding this specific buffer, right? So you have this buffer, and then we're saying, okay, you know, for this attribute, whatever the buffer that's currently bound is this. If we have multiple buffers, then depending on the one we bind, we're going to get a different shape, right? Different set of vertices are going to be set. So imagine having now color buffers and positions and whatnot. You don't want to bind every single time. You just want to bind one thing and then it gets all the correct stuff. And this is essential videos, which we'll do next time, but I think this is very good for now. Let's try to do just the square, make sure that this works. So on the top left, can we draw two triangles? So on the top left is minus 0.5, and then 0.5, which is on the right, and then bottom left is this, correct? And then the other triangle, which is from the top right first. Top right is this. Nice, so it's this one. Wait, so this is top left, and then top right, yeah. Then top right. Yeah, if we cut it up like this, this is top right is this 0.5. And then bottom left is this, okay. And then this time we start top right, bottom right, and left. Now, if we keep it this way, it will work. Where is this thing? Well, here we don't have 3 vertices anymore, we have 6. So here we can say len vertices. That should be, why is this complaining now? Okay, sure, give you 32. Okay, so you have this many vertices. Now if we keep it and we keep here only 3, I think it's going to load all 6 vertices, but it's going to only draw 3 of them. No, it's failed, completely failed. Either this is wrong or, okay, let's do 6 and see if this works. Nope. Okay, let's go back to the vertices. What's this? Oh, that's the stride, sorry. Strides shouldn't change. Oh, okay, we're already doing length here. It's fine. All right. So only in this place, if we keep 3, I think we'll only get the first triangle, first half. Yes, there you go. So it's only looking good, only telling it, hey, take 3, start at 0, up to 3, draw this. We can actually do this in 2 times, I think. Next time, 3 to 6. 3 to 5, 3, 4, 5, yeah, 3 to 5. Let's see. I think this be 2. The first, oh, and the count, not the last, not indices. So the count, so this is 3. So starting at 0 and then count 3, and then starting at 3, count 3. Let's see. Yeah, we got this, the full thing. Or of course, we can just do it 0, but we have 6 of them in one draw column. There we go. And yeah, we can do all kinds of crazy things now with this. It'll be awesome next time. All right, thank you all for coming. This is very good progress. And I think we're getting close to actually being able, if we abstract all of this out, then we'll have the first part, or maybe the second part after the inputs of the game engine, where now we can have some shaders in a very nice way and draw stuff. Maybe next we can do model loading, so you can load a model and without doing vertices by hand, we can just say draw this thing and it draws that. Yeah, thank you all and have a good day.